Welcome back. In this section, we'll be talking about the second derivative test and what the second derivative tells us about the graph of our function. So first off, we've got our function f, and it's defined on some interval, and we're assuming that the derivative exists too. If it turns out that our derivative is increasing, of course, what does that mean for us? When I say that the derivative is increasing, I'm talking about the rate of change of the derivative. In other words, I'm talking about the second derivative. So if I say the first derivative is increasing, I'm really talking about looking at the second derivative and asking, is that positive? Of course, that's what the first derivative being increasing would mean. Now, what does that mean for us for our graph? Well, if the first derivative is increasing, we have that our graph is concave upwards. And we can sort of see that in this little graph here, that from about 1 and onwards, the shape is like a parabola opening upwards. We would say that that part of our graph is concave upwards. And you could also see that in terms of slopes. At around 1, our slope is negative. And as we start moving further to the right, the slopes are still negative, but a little bit bigger, a little closer to 0. Then bigger still, our slope is 0. Then larger still, now our slopes are positive. So as we move from 1 onwards, our slopes start out negative, then getting bigger and getting to 0, and then getting larger and becoming positive until our slopes become very large. And of course, the opposite is also true. If we have our function has a derivative that's always decreasing, then we'd say that the function is concave downward. And in our graph, it's concave downward until about 1. And we can sort of see the same sort of business going on with slopes with this. We start off with our slopes are quite positive. And as we move further to the right, the slopes are getting a little smaller and smaller, and then eventually our slopes are 0, and then eventually our slopes are negative. In other words, our slopes are decreasing as we move our way from left to right. And so we have that concave downward shape. So again, it's the second derivative really that's telling us this, because the second derivative is telling us whether the first derivative is increasing or decreasing, just like how the first derivative told us if our function was increasing or decreasing. So here's our test for concavity. If we happen to have a second derivative that's positive, then that's telling us our first derivative is increasing. And of course, if your first derivative is increasing, then your function is concave upwards. And the opposite is also true. If we have our second derivative is always negative, then that means our first derivative is decreasing. And if our first derivative is decreasing, then our function is concave downward. So basically the same sort of ideas that we use for finding where a function was increasing or decreasing, we can use those same sort of ideas to find where the function is concave up or concave down. We know that really things are going to depend on where is f double prime, where is that positive, where is that negative. So we'll figure out where is f undefined. We'll also figure out where is our second derivative either 0 or undefined, because all those places are places where maybe our second derivative could be changing from positive to negative. And then now that we've done that, we've got our number lines split up into a bunch of intervals, and then in each interval we'll pick a value, test it in our second derivative to see whether it gives us something positive or negative, and then use that to draw our conclusions. Okay, so we've got a function, and we want to know where is this function concave up or concave down. And so we're going to start off by first finding our derivatives. So first derivative for this function, I have 6x cubed minus 9x squared. So finding my derivative, I have 18x squared minus 18x, just using my power rule. And then the second derivative is 36x minus 18. Now f of x, this is a polynomial, so it's defined everywhere. And for our second derivative, that's also a polynomial. It's also defined everywhere. So the only places that I would need to concern myself with would be places where we have the second derivative equal to 0. So I guess let's look at that. Where is my second derivative equal to 0? And I find there's only one place where my second derivative is equal to 0, and that happens to be at x is equal to 1/2. So I guess now what I'll do is make my number line. And as I said, on our number line, we'd put any place where f was undefined. We don't have any of those. We'd put any places where our second derivative is undefined. Don't have any of those. We put any place where our second derivative is equal to 0, and we've got one of those, and that happens to be at 1/2. So it looks like there's only two intervals to look at, things less than 1/2 and things bigger than 1/2. As always, I'm going to choose nice numbers for myself. So less than 1/2, I'll choose 0. Larger than 1/2, I'll choose 1. And then we'll find out what happens with our second derivative. So at 0, our second derivative is 36 times 0 minus 18, which gives us negative 18. And since our second derivative is negative, that means we are concave downward. In other words, we have that parabola opening downward kind of a shape going on. And if we are larger than 1/2, if x is equal to 1, then our second derivative at x equals 1 would be 36 times 1 minus 18, which is positive 18. So we are concave upwards. And that is that kind of a shape, parabola opening up. So there we go. That's where our function is concave up and concave down. We can just write this a little summary at the bottom. So concave up on the interval from 1/2 onwards, and concave down from the far left up to 1/2. Okay, let's do another one. This is a function, we've seen this one before, but from I think it was 3.2. But let's pretend that we haven't seen it and start from fresh and take our derivatives and deal with this. First thing before I get into taking derivatives, I'm just going to make a little note to myself that I know that this is undefined at x equals -2. So I know that -2 is going to need to show up on my number line because that is a place, any place where your function is discontinuous or undefined, those are places where you could change concavity. So -2 definitely needs to show up on my number line. Let's get going with our first derivative. And for that, I guess we need to use our quotient rule. So let's get into that. Denominator gets squared. X plus 2 cubed, when I square that, it gives me x plus 2 to the 6. And then the bottom comes up. Derivative of the top minus the top as it is, and then derivative of the bottom. And then I'll do a little bit of cleaning up. I notice I have a 3 that I can factor out of both terms, and x plus 2 squared that I can factor out of both terms. So that leaves in the first term just a single x plus 2. And in the last term, I have just the 3x plus 2 left behind. And then I can do one little last bit of cleaning things up here. I can see that the x plus 2's, I can cancel those out. And I can see then that what I've got inside my bracket, I'll have x minus 3x, so that's -2x. I'll have 2 minus 2, the 2's will be gone. So my first derivative simplifies to give me -6x over x plus 2 to the 4. So first derivative, we found it, and now we need to go on and find our second derivative. Since the first derivative gave us a quotient, again, quotient rule is going to come into play. So second derivative. And let's get into it. Bottom is getting squared. X plus 2 to the 4, when I square that, that gives me x plus 2 to the 8. And then bottom comes up, x plus 2 to the 4, times the derivative of the top. Derivative of minus 6x is minus 6. And then the top as it is, times the derivative of the bottom. Derivative of x plus 2 to the 4. Okay, and then again, I've got some common factors. I have the minus 6 I can take out of both, and the x plus 2 cubed I can take out of both, leaving an x plus 2 in that first term, minus, then there's the x times the 4, and that's kind of about it. Okay, a little bit of cleaning things up here. I'm just going to cancel the x plus 2 cubed with 3 of the x plus 2's from the denominator, leaving x plus 2 to the 5 in the denominator. And then what I'm going to have after all of this, inside the brackets, x plus 2 minus 4x, all of that cleans up to give me minus 3x plus 2. And when I multiply the negative 6 in, it'll give me 18x minus 12. There we go. We've got our second derivative nicely found. We're good to go. And the only thing I need to do next is solve for where is my second derivative 0, and then use my number line. So for the second derivative, if I'm looking for where is that equal to 0, I know that the second derivative is equal to 0 whenever the numerator is equal to 0, and that's because for a rational function, fractions are only ever equal to 0 when the top is equal to 0. So 18x minus 12 equals 0, and that gives me one single value for x where my second derivative is 0. So 12/18, or same thing as 2/3. So we had two different numbers now that we need to put on our number line. We have on our number line the 2/3 that we need to put on. We also need to put on the other value, which is where our function was undefined. That was at x is equal to -2. So we have then 3 regions for us to investigate. Things larger than 1. So for things larger than 1, I'm going to go for things larger than 2/3, I'm going to go for 1. For things between -2 and 2/3, I'll go for 0. And then for less than -2, I'll go for -3. So away I go. I'm going to now figure out for myself what I've got for f double prime of 1. So if I put in 1 into my second derivative, I would have 18 times 1 minus 12. I'd have 6 on the top. I'd have 1 plus 2 to the power of 5. I'd have 243. So 6 over 243, that's 2 over 81. We are positive, so that means we are concave upwards in that region. For my second derivative when x is 0, f double prime of 0, I'd have -12 for the numerator, and I'd have 2 to the power of 5. I'd have 32 for the denominator, or -3/8. And so that would be then concave downward. There we go. So we're concave downward in that region. And then for -3, I have for the numerator I'd have 18 times negative 3 minus 12, which gives me negative 66 on the top. And in the denominator, I'd have negative 1 to the 5, which is negative 1. So I'd get positive 66. So we are concave upwards in that interval as well. So now I can make my little summary down at the bottom. I can say we are concave up in two places, from the far left all the way up to negative 2, and from 2/3 to the right. And where are we concave downwards? Just in the middle between negative 2 and 2/3.